Okay, this is where we were in the last class. Okay, yeah. So yeah, this is where we were in the last class. We were trying to look at the all the normal forms where the functional dependencies are involved, right? Uh, we looked at what a relation is and what are the attributes in a relationship, and we looked at what are the functional dependencies between the attributes, and we looked at the all the three normal forms: first normal form, second normal form, third normal form, and BCNF. Okay, right. Now I gave this and left last time here where I gave the property record, and I said there's a property number, city, house number, area, price, and tax. Okay. Property number is the unique number that you give for the property, the house property. City is the city where the property is located. House number is the house number within the city. Then area is the area of the property. Price is the price of the property. Tax is the tax no, that is charged for the property in the city. Okay. There are two candidate keys to identify this property record. One is a property number that's going to be unique. So every property is going to be identified uniquely. Okay. I'll insert one more slide and then just put this there. For example, examples for this are the property record with some unique number. For example, let us say I'll give some 4-digit unique number for the property. Okay, city is Chennai. Okay, house number within Chennai is, let us say, 210. Okay, then we were saying area. Area is, let us say, 450, square foot. Price is, let us say, is 1 lakh. Okay, rupees, and the tax is, let us say, is 300. This is what the record that we are talking about. What are the functional dependencies in this record? Okay, this is what property number is going to be unique. So there not going to be any other record with the same number 1101. Okay, so this will not be repeated in the property record. So this will uniquely identify the property record. So that's a candidate key. Similarly, the city and the house number. City is Chennai and the house number is 210. Again, this won't get repeated because this together you will give a unique ID, which is the property ID. So this is also a candidate key here. Okay. City and house number is also a candidate key. Okay. Area is what we were saying. Area is 210 square foot. For no, sorry, this 450 is the area. Price is this for this area 1 lakh, and tax is area, price, and tax. Okay, right. So area is whatever square feet, price is 1 lakh, tax is whatever we indicated there. Okay, so these are the two candidate keys. They'll uniquely identify city plus house number is one candidate key, property number is one candidate key. What are the FDs now? Functional dependencies. The property number will uniquely identify the city, house number, area, price, and tax. Okay. Similarly, the city and house number also will functionally determine the property number, area, price, and tax. So all the attributes, are dependent on property number and city and house number. Okay. Area also determines the price. Given an area, square foot or whatever it is, that will determine the price of the property, not the city, which is unrealistic. Normally, the city also, based on the city, the price will vary. But right now, we are assuming that all the cities, for other calculation purpose, like tax calculation purpose, across the whole of India, given an area, we will fix the price. Okay. Similarly, given a tax, given a city, we will fix the tax. For the whole city of Chennai, there will be one tax. For Mumbai, there will be another tax like this. So this is an example. What we asked you last time to identify is which normal form, what are the normal forms that it is in. Okay, this is where we stopped in the last class. Okay. Can somebody tell me which normal form it is in? Is it in second normal form? Obviously, it is in first normal form, right? Every relation, which is all these attributes are atomic, they are not divisible further, right? So, trivially, this is in first normal form. Okay. Now, let me ask the question: is this in second normal form? Can somebody answer? Is this in second normal form? Is this relation in second normal form? Is this relation property record, is it in second normal form? What is the condition for second normal form? I'm just looking at the chat box to see if I get any answers. Is this in second normal form? What is the condition for second normal form? What is the condition for second normal form? Is this in third normal form? Is this in third normal form or in BCNF? Hmm? What is the condition for second normal form? Non-prime attributes should not be partially dependent on the key attributes, right? All the prime attributes should be fully dependent on the key attributes. So now can you answer all, which are the non-prime attributes here, which are not part of the key? Area, price and tax. These are the non-prime attributes because they are not part of any candidate key. Okay. Now what is the condition for second normal form? Non-prime attributes should not be partially dependent on the key. Now, does this satisfy the second normal form? Is this going to satisfy the second normal form now? Are there any answers coming for me? Is anybody trying to answer the question for me? I'm looking at the chat box. Okay, I'm not getting any answers. So I don't know how to actually take that. Okay. So this now you have the city, okay, which is part of the prime, which is partially no in the key, right? City determines the tax. This is an FD, right? Now city is part of okay the key, okay, city plus house number, okay. Hence city, yeah, no, the attribute tax attribute is, which is non-prime attribute, which is not prime attribute, is not part of the key. Okay, non-prime attribute is partially dependent on key attribute city. Okay, not the full key, partially dependent on the key attribute city and house number. Hence, not in second normal form. Okay. Obviously, once something is not in second normal form, it is also not going to be in the right? It's also not going to be in the third normal form. Okay, which are the things that are violating the normal forms? Which FDs will violate? This will violate the second normal form. Which are the things which FDs will violate the third normal form? The third normal form says that every functional dependency, the left side has to be a key, a part of the super key. Left side is either a super key or right side is part of a key. Okay. Now look at the which FDs will violate this. Okay. FD1 property number fully determines all the other attributes, and hence this doesn't violate the second normal form. Does this violate the third normal form? This FD also doesn't violate the third normal form because property number is a key. So the left side is actually a part of a left side is a super key. LHS is a super key here, which is also a key, right? Key plus something more is a key. So obviously, this is left side is actually a key in particular case, and hence doesn't violate the third normal form. Okay. Does this violate BCNF? BCNF requirement is that left side has to be a super key. So FD1 doesn't violate any of the normal forms. FD1 satisfies functional dependency. FD1 satisfies all the normal forms. That is 1NF, 2NF, 3NF, and then BCNF. Okay. Now look at FD2. FD2 also is same. City and house number, area, price, and tax. So city and house number is a key now. Okay. So this satisfies since the key attribute fully determines all other non-prime attributes, it is in second normal form. Since all of them are atomic, first normal form is satisfied. Okay. Then since the left side is a super key, 3NF satisfied. Since the left side is a super key, BCNF is also satisfied. So FD2 satisfies all the normal forms. Okay. One NF, 2NF, 3NF, and BCNF. Okay. Right. Now go and then look at area and price. This is big 3. Okay. This is area is not a key. Satisfy the first normal form because area and price are basically atomic. Does it satisfy the second normal form? This FD will satisfy the second normal form because this has nothing to do with prime attributes. Area is not part of the prime attribute. So this will satisfy the second normal form. Does it satisfy the third normal form? Area is the left side of this functional dependency. Area is not a key in this relationship. Area can get repeated. So it doesn't satisfy, or the price has to be part of a key. Is price part of a key? Price is not part of a key, and hence this doesn't satisfy the 3NF. For BCNF will require area has to be a super key. So FD4 doesn't satisfy 3NF and BCNF. Okay, FD3 doesn't satisfy. Does not satisfy 3NF and BCNF. Any one that satisfies BCNF means that it will satisfy all the other requirements. Okay, right? If some relay FD is in BCNF, it means that it's also in 3NF because the LHF would have been a super key. That also means that it is going to be in 2NF because the key attribute will fully functionally determine the other attribute. Okay, and it will also will be 1NF because it's atomic. Okay, right? Similarly, go to FD4. FD4 is city determines the tax. City is here part of the key. It is not super key. It is part of the key. Super key means key plus something more. City, house number, area will be super key. City is only sub part of the key. City plus house number key. So city is part of the key. This city determines the tax. Okay. Now if you look at this FD, this doesn't even satisfy the second normal form, because city is tax is partially dependent. That non-prime attribute tax is partially dependent on city, which is the prime attribute. So it doesn't satisfy the second normal form. Obviously, it is also not going to satisfy the third normal form, because this is not key, not super key. Neither tax is also not part of the key. So this doesn't satisfy the third normal form. This also doesn't satisfy BCNF, because city is not part of the no. Okay. So FD4, okay, doesn't satisfy. FD4 does not satisfy satisfy 2NF requirement, 3NF requirement, BCNF requirement. Since FD4 violates even the 2NF requirement, the whole relationship having these functional dependencies is not in second normal form. Okay, so that is what the answer for this. Given this property record, and given these are the two candidate keys, given that these are the functional dependencies, this relationship is not in second normal form. Okay, is that clear? So that's the answer for that. Okay. Okay. Right. Okay. So I'm not getting the answers, so I'm giving the answers. Okay. If you have any doubt on this, now please ask in the chat box. Raise. If you have any doubt, please raise it in the chat box. Okay. I showed you that this relationship having the following dependencies, in which normal form it is. Okay, right? So given a relation, given the functional dependencies, you can determine which normal form it is in. Okay, I'm going to give you one more exercise now. I expect you to actually solve this exercise. Okay, I do the along with I will also do the exercise before I go to 4NF and 5NF. I want you to solve some problems along with me today, so that this concept is very clear for you. Okay, if you have any doubts, please raise it at this point of time. If you have any doubts on solving this problem, okay, given this record, given this relationship with the following functional dependencies, we saw which normal form it is in. Okay, right? Okay, is that clear, or no? I should go over this again. I'm going to give you one. Okay, give you some time and give you the answer, because I want you to. This is a very important concept. Okay. I don't know whether I put more example here. Okay, I think I have actually not in 2NF. These are these are into the slides. Okay, more examples. Okay, now take this one. Okay, and tell me which normal form it is in. Train record, train number, origin station, destination station. Okay, where the train is originating and where it is going, which zone the train belongs to, and the manager of that particular zone. Okay, right? Now the given functional dependencies are train number determines the origin, destination, zone, and manager. For example, we can say Godavari Express. Okay, Godavari Express origin is Visakhapatnam, destination is I think it's Hyderabad, right? And then zone is South Central. Some manager is some Tripathi, some guy. Okay, so train number determines the origin, destination, zone, and manager. Okay, right? Where the train is originating, that also determines the zone. For example, this train originates from Visakhapatnam. Then the zone is South Central. Okay. The zone also determines its manager, because each zone has a manager. Given a zone, this determines the manager. Okay. Now, given this, can you now tell me which normal form this relation is in? Okay, this is an exercise now. Okay, if you have any doubts, you can ask me. But then I'm going to give you 2-3 exercises like this for you to be able to solve them. Okay, right? So can you now put your answers for which normal form it is in? Okay. Are there any doubts on normal forms? I've just finished normal forms up to BCNF. I'm going to solve some problems for you, but then you should tell me if you have any questions on the normal forms. Okay, right? Can a college solve this problem and tell me which normal form this relationship is in? I'm going to share with you also a tutorial sheet. Okay, I'll make you do some problems today and share a tutorial sheet based on this so that you can solve them yourself. More problems you can solve and then identify. Okay, and the normal form concept is clear for you. Okay, right? Are you guys with me? Can Vijayanagaram campus, can you put up your answer? Are you trying to solve the one? Which normal form it is in? Put it in the chat box. Which college? We'll now run a competition across colleges and see which one is able to give the answer to us. Okay, with the reasons. Then we'll declare that college as the winner. Okay. I'm trying different techniques. Okay, make the colleges participate and fully understand. Okay. Which normal form it is in? The previous relationship. Should I give the answer myself? No college is a winner in this. Hmm? How do you determine which normal form it is in? Thought some colleges will at least give me the answer. Hmm? Given that these are the FDs, No, does the first FD problem is not visible? Why is the problem? I'm sharing the desktop. Why are they saying the problem is not visible? Is the problem visible now? Yeah, if I switch into the no, I think if I bring up the A view, I think I'm not seeing the answer. Okay, if I want to see the answer, bring up the A view. Okay, then I think it becomes a problem. Okay, let me see if there is a you are visible, not the PPT. Is it? Problem is not visible. Who is saying user one? Who is this user one? Not in 3NF. Okay. Why is it not in 3NF? Yes, Vijayanagaram campus has got the answer. It says that not in 3NF. Why is it not in 3NF? Which FD will violate the 3NF? Oh, user 1 is Jntuk Kakinada, is it? Okay. Okay. I'm visible, not the PPT. That's not correct. I'm not visible, I guess. Chakravarti is, I started sharing the desktop. Is the desktop visible now? See, this is the origin is not the key. Okay. Origin is not key to this. Train number is the key, right? Origin is not the key. Okay. Right? Or which is the requirement for 3NF? Origin is not the key, is not enough. Origin is not the super key. That's right. You have to write it correctly. The reasoning has to be correct, right? Origin is not super key. Okay? Right? That's a requirement of 3NF. Or what is the requirement for something to be in 3NF? Origin is not key or what? What is the requirement for 3NF? No. What is the requirement for 3NF? 3NF requirement is LHS is super key or RHS is part of key. So now here zone is not part of the key. Okay, that's why it is not in 3NF. Okay, what is the 3NF requirement? 3NF requirement is LHS is a super key, origin is a super key, or zone is a hello. Sure. No, no. Actually, we are only looking at one FD. We are not looking at multiple FDs put together. Okay. If this FD is violating the what are the? It is violating the 3NF because origin is not a super key, LHS is not a super key, or RH is not part of a key. Okay. So this is actually violating the 3NF. Okay. That's what we want them to. That's what we want them to identify first. Okay. So obviously this is not in the. each of the FDs, I want them to identify which normal form they are violating. Okay. Okay. Right. Okay. Okay. So, right. So this is not in 3NF. Okay. Right. This violates the 3NF requirement. This satisfies all the requirements. FD1 will satisfy all the requirements. Okay. Because train number is a super key which is a super key. So it will satisfy 1NF, 2NF, 3NF, and BCNF. Okay. This one will not satisfy. Both origin and zone are not prime attributes. So this will satisfy the 2NF. Okay. Now zone and manager, if you take this dependency, again this will violate in the same way as origin and zone, this will violate the requirement for 3NF because zone is not a super key for this relationship, or manager is not part of a key. So this also violates 3NF and obviously violates the BCNF also. Okay, right? So this is now what is this relationship is in? This relationship is in 2NF. Okay, this relationship. The answer is this relationship is in 2NF. Okay, this is not in 3NF because these two FDs are violating the 3NF. Okay, suddenly it is also not in BCNF. Okay, is that clear now? How to look at the normal forms? So this is given this relationship, given the FDs, this is in a 2NF. This is not in 3NF or BCNF. Okay, I will do one more example here. Okay, an abstract example I do now. Okay, for just making sure that you understand. Okay, one more example to just this is an abstract example. Okay, but this has nice other things. Okay, we'll take only 3 attributes in the relationship. Okay, now we'll say the FDs in this are A, B determine C. Okay, and then okay, C determines A. Okay, C determines A. Okay, given these FDs, now identify which normal form it is in. Okay, right? Now AB together will determine C. C determines A. Okay, this is an abstract relationship R having A, B, C as the attributes. Okay, now we want to find out which normal form it is in. Okay, right? Now first, how will you determine the candidate keys for this relationship? You will do the attribute closure, right? If you just take A, what is the how will you solve this? You will just take the A to start with. If you take A and then do the attribute closure of A, what is the attribute closure of A? Attribute closure of A is, what is the answer for this attribute closure? What is the attribute keys that can be inferred, and then what becomes now the closure set for attribute A? We'll compute the, if I get an answer, it's fine. Otherwise, I'll solve the problem myself. I'll keep looking at the answers. Okay. Using the attribute closure, you will determine the keys. Once you determine the keys, then you know in what normal form this relationship is in. In the previous example, I gave the keys. Okay. Now, using the attribute closures, you can determine what are the keys for this relationship, right? Given FDs, you can say which are the candidate keys for this relationship. How do you determine the attribute closure? Given A, which are the, I'm not getting the answer for this. I guess I've done this. Attribute closures I've done previously. How do you compute the attribute closures? This is given R, A, B, C, and the following functional dependencies. The closure is A only. Yes, this is excellent. So why A only? Because none of the other functional dependencies can be applied using the, okay, there's no other functional dependency that can be applied starting from A. Okay, what is the closure for AB? Okay, closure for AB is, if you take AB as a starting attribute set, then the closure is A. You can now use this. I think I will just look for AB is the key, right? User 1 is giving it, yes, this becomes ABC now. Okay, ABC, this becomes the closure for this. Okay, sorry, and this is the full attribute list of the relation, right? So you can see once you take AB, you are able to get all the full list of the attributes relationship, and hence AB is a candidate key. Is there any other candidate key for this? AB is the key. Is there any other candidate key? AB is one candidate key. Is there any other candidate key for this? Is there any other candidate key for this? If you also start with what is the closure for BC? Now for BC is also, you can apply C to A. Starting from B, C, you can apply A, right? So the closure is B, C, and then A. Okay. So BC is also a candidate key for this. No? 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 Right? So you have two candidate keys for this. Is there any other key other than these two? Okay. Somebody is jumping the gun. Okay. Right? No? Yeah? No? 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 Yes. So why is this? It is in 3NF, this relationship. So if you look at the AB determines C, okay, this is satisfying the requirement of both BCNF and 3NF, right? Because the left side is a key for this relationship, right? But then C to A, C is not a super key, but A is part of the key. If you look at this FD, A is part of a key, right? So this first FD is satisfying both 3NF and BCNF requirement, whereas the second FD is satisfying only 3NF requirement. Okay, right? So the relationship is in 3NF. Okay, user 1 has got it right. Okay, I will modify this and then give just one more this thing to see if you can actually solve this problem. Okay, C to D and D to A, and just quickly compute which normal form this is in. Okay, okay, just compute this. I think after this we'll go to 4NF, multi-value dependencies and all of that. Can you just see which normal form this is in? Can I get an answer? Now we'll stop user 1 from responding. We'll see if any other college can respond for this. Say which normal form this is in. This is in 2NF. Excellent. Vijayanagar campus is actually. Why is this in 2NF? Can you just put up in the chat box so that we can all see? AB is the key. Okay. There's no other key other than AB. What are all the keys for this? Only AB is the key. BC is also a key, because if you start with BC, D and A will come, and then that includes the rest of it, right? Okay. BC is another key. Any other key? Is BD also a key? Is BD also a key? Not getting the answer back from them. If you start with B and D, B, yes sir, yes, B, right? If you start with B and D, then D and D, this will include A, right? Then you get A and B, that includes C, okay? So it is actually a key. BD is also a key, right? Is that yes? BD is also a key for this, because if you start with B and D and try to do the closure of this, okay, then you will get actually B from D. If you take this dependency D to A, okay, A can be added here. Once you add A, okay, A and B are now there. A and B will determine now the C, so that becomes C now. Okay, so this also becomes a closure for this. Okay, right? Now, which of these FDs will violate the 3NF? Is it in 2NF? This relationship is in 2NF. Can you put that answer why this is in 2NF? You gave the answer, it is in 2NF. Why are you saying this relationship is in 2NF? Now you know all the keys. Okay. Now I am getting answer from user 1. Okay. See the FD2 is violating what? C is not a key. Okay. Does this violate this 2NF? What does it violate? It violates the 3NF. Okay. Right. It is in 2NF because no non-prime attribute. Okay. Which are the non-prime attributes here? Which are the non-prime attributes? What are all the keys? BC is a key. Okay. BD is also a key. Okay. What are the keys in this? Key attributes. All are prime attributes. Correct. Okay. So obviously, since all of them are prime attributes, there is no non-prime attribute. So there is no problem with 2NF because 2NF is defined with non-prime attributes being partially dependent on prime attributes. So there is no problem with prime attributes here. There is no non-prime attribute. So this relationship is in 2NF. Why is it is not in 3NF? It is not in 3NF because this FD C to D, C is now yes. See, user 1, what I am seeing is you are talking about transitive dependency. Okay, LHS of every FD is a super key. This is a requirement. Okay. Now 3NF requirement is LHS of every FD is a super key or RHS of the FD of the FD is part of key, is part of a key. This is what we are defining. Okay, right? You are going in a slightly different way of looking at the transitive dependency. Okay, right? I can come back to that, and then I don't want to confuse the rest of them with the other interpretations. Okay, given an FD, conditions should be satisfied either or. Okay, now for BC and F, we don't allow the RHS part. For every FD, LHS has to be a super key. Okay, for 3NF, relaxation is that if the RHS is part of a key, then we will say that it is in 3NF. Okay, I've actually explained why the dependency preservation becomes a problem if RHS of an FD is part of a key, and that's the reason why if a relationship sometimes you have to relax and you should not make every relation into BCNF. I'm going to come back to that. Okay, in a minute I'm going to come back to that. Okay, but now which parts of it will violate the 3NF requirement? The 3NF requirement is if C is not a super key, D has to be part of a key. Is D part of a key? Yes. What about D and A? D is not a key alone, but is A part of a key? Is A part of a key? Yes. So now, will you modify your original answer for this? Which normal form it is in now? Is this condition satisfied for all the FDs for 3 and F? Is the first functional dependency satisfies the 3 and F requirement? It also satisfies BC and F requirement. Okay. AB is a super key. Okay. The second one doesn't satisfy the BC and F requirement because C is not a, the LHS of the functional dependency is not a super key. Okay. But the right side, RHS is part of a key. Similarly, this functional dependency also satisfies the 3NF requirement. So, which is the normal form it is in? Have you got any doubt now? If people have doubt, they should sit now. So, I can also come. Now, I'm doing a remote class. That's why I'm taking an example and trying to look at every part of it. If you have a question, please put it in the chat box. Okay. Will you modify this normal form? Would you take time to actually relook at it and come back? Should I come back? Or is that clear now? Which normal form it is in? Will you say it is in 2NF or 3NF? Jntu Vijayanagaram campus is not answering now. If there is a question, please put it there. I'll answer it for you. Okay. Is that clear or not clear? The closure part and keys for the relationship, is that clear? As per my version, it is in 3NF, right? What about your version? What version? No, according to you, which normal form it is in? See, this is what I want you to tell me. If I'm making a mistake, that's where you will learn. Okay. This is no, it came as 2NF. Okay. What is the reason why it is in 2NF? Okay. JNTU K8 is also says it is in 2NF. Okay. Now, what is the 2NF requirement? What is the 3NF requirement? Okay. 3NF requirement is that every FD has to be Yes, we're deferring the discussion on the transitive dependency, okay, right? The reason why we are deferring the, okay, we'll come back to that, okay, I'll sort of take it up, and I think A8 is also saying that it is in 2NF, okay. See, I want you to understand, see, we want you to go a little deeper and start understanding. That's why we are trying to make you think, okay, right? If the keys are already given here, right, what are the keys for this relationship? The keys for this relationship is, we know that AB is the key, okay, for this relationship, and then BD is the other key. If I have a board, it would have become easier for me, okay. Now I'm actually, sorry, BD is also a key because we are taking B and D. And then what is the other keys that we have? We have also got B and C as the key, okay, right? Understand intuitively what is the what is the requirement of a normal form, okay. If it is in BC and F, these are all the candidate keys for this relationship, right? Now the simple understanding of a BCNF is there's not going to be any duplication caused by these functional dependencies if it is in BCNF, because every dependency, every functional dependency is reflected as a key, super key. That's what this is saying. LHS of every FD is a super key. That's what the BCNF will say. What you are saying is now the 3NF, the 3NF requirement as I have defined it, as I want you to understand, is that the LHS of every FD, functional dependency, is a super key. That's one requirement. Or the RHS of the functional dependency is part of the key. Okay, right? I will sort of show you why this requirement. Okay, what is being now seen here is there is a transitive dependency C to A that will become the F closure. If you basically write the functional dependencies closure, there is lot more functional dependencies that you can write for these functional dependencies. By using the Armstrong axioms, you can now put augmentation rule, you can put more functional dependencies, transitive dependencies, you can also infer now C to A from this, okay. That's also part of, now C determines D, D determines A, so C determines A. So that also becomes a transitive dependency, okay. Now if you put the F closure of this, you will get all the other dependencies as part of this relation R, okay. Now the condition is whatever FDs that are there here, okay, if the FDs don't satisfy the LHS part, LHS of every FD is a super key, okay, then there is going to be a redundancy now, because the RHS of the FD being a part of a key, we will relax now, saying that look, I will permit 3NF will now suffer from a duplication of this FD not being taken care of, okay. In fact, I have a simple example here which we are doing, okay. Now look at this train example, okay, which we have put previously, okay. Now we have this 1261 train number. I think this is Chennai Delhi Tamil Nadu Express. Zone is South Zone. Manager is DK Singh. Okay. Now you look at this number. This number is actually, I think, the this is the Grand Trunk Express. Again, Chennai Delhi. It is South, and the manager is also DK Singh. Okay. Now this is Vizag Delhi. I think this is the Andhra Pradesh Express, the new Andhra Pradesh Express. South Central and some name I had put. These names are fictitious names. They are not the real names. Whereas these are the real names. Okay. Now, when we said origin city, train number determines all this. This functional dependency will not get duplicated because the train number is a key. This will never get repeated. Now look at origin city to zone. Okay. This is the functional dependency, and this is not the key in this relationship. So this will get repeated. As you can see, Chennai South, Vizag South Central gets repeated. Any FD, the LHS is not a key, will cause duplication of data. Similarly, look at this zone and manager. This is an FD. This zone is not a key. So the South being DK Singh, South Central RMK Shastri, South Central RMK Shastri. Actually, you can see that this is, this also causes duplication. So if you look at BCNF requirement that every FD, the left side LHS is a key to the relationship, ensures that there is no duplication. So if you take a relationship to BCNF, okay, there is no duplication. Okay, the LHS of every FD is a super key. Make sure that there is no duplication. For example, if you actually split this, now this is the relationship, this is in BCNF. Okay, train number Chennai, Chennai, Delhi, Vizag, Delhi, and Vizag, Hyderabad. This is the train number. Okay, right? Now, if two trains originating at the same city and going to a destination city, since the numbers will determine, we don't put this as a functional dependency. So train, we are not further saying that no, there is a dependency from the train number to the train number in terms of different train numbers starting in the same location. Okay, right? So if you go further down and look at this, this will now be split into city and zone. That FD is split now. Chennai, Vizag, the zone is south and south central, the manager. So this will not suffer from any duplication. Okay, the original one has the FDs cause duplication. Okay, now if you 3NF will cause duplication. Okay, because if you look at an FD, the LHS of the FDs is not a key always. It can also be that the RHS is part of a key. Okay, to make you understand this, I will do a simple BCNF violation which I did previously. Okay, which is in 3NF but not in BCNF. Okay, right, to just make you understand. Then come back to this example. Okay, sorry. A board would have made things simple for me. Okay, keynote, insert, slide. Okay. Just take this example. R, A, B, C. This is what I've done. Just get it here. Okay. Take this FDs in this as A, B, determining C, and C determining A. This is something that I did previously. Okay, this has a nice property. This where we were saying that AB is the key for this relationship, right? Now this relationship is in 3 and F. Why is it in 3 and F? Because the C to A, the C is RHS, the C is not key, but then sorry, the A is RHS, which is the key, which is AB is the key. Okay, C is not a super key, so it is suddenly in 3 and F. Okay, now try to make it into BCNF. The only way you can split this for bringing this into BCNF is you can put it R1 as one relation, right, and then R2 as the other relation, where you get the P and C. Okay, right? Now this doesn't preserve the dependency. This doesn't enter the dependency preservation, because now you can see how will you preserve the dependency A, B together will determine the A. Okay, here. Okay, sorry, C. Neither this split or this split will preserve this dependency. Okay, right? So this is where the 3NF is saying, look, since this dependency of the A being part of the key, Okay, this A is already part of the key. Okay, now to preserve this dependency, if you split the you can also make it into A and C. Okay, probably this dependency A and C. This also doesn't preserve. Whatever split you make further, this doesn't do the dependency preservation. Okay, so if you look at a relationship, you start with what is the way this whole thing will work now. Even though this causes a duplication, okay, this is understanding now. Though this causes duplication, we will not further want to go into BCNF. If you split this relationship into BCNF, it is not possible for you to preserve this dependency, AB determining C, okay, right? Only when you join it, AB and AC are joined, and then you create a new relationship. Then I think you can check for the dependency here, AB, determining the C. Okay. So the idea is you will go to BCNF, okay, with dependency preservation. This none of the dependencies should be lost. If you're splitting and losing these dependencies, then you don't want to actually BCNF with dependency preservation. Otherwise, you're going to stop with 3NF, okay, and not get to BCNF if dependency cannot be preserved. Okay, this is where 3NF is saying, look, if the right side is basically a key, now stop there. If you problem with this dependency preservation by getting into BCNF, okay. Otherwise, every relation we want to make it into BCNF. The requirement is the LHS has to be a super key, okay. Now, in cases where the dependency preservation is a problem, the LHS has to be a super key or RHS has to be part of a key. That's what is the relaxation that is being provided for 3NF. Suddenly 2NF, since the dependencies among the non-prime attributes are not at all checked, if there are dependencies of duplication, 2NF will suddenly cause duplications. 3NF will cause duplication if, for example, this dependency, if the C is not the super key, it will cause dependency, it will cause duplication. BCNF will never cause duplication. There is no duplication of data when a relation is in BCNF. BCNF ensures that there is no duplication of data. But only problem is when you split with this additional dependency coming in, C will, this A is not part of E. Imagine this is typically the same case as we were seeing here in the journal manager case. Okay, look at this here. The origin city is the zone. Zone is determining manager. Okay, right? Now this zone determining the manager is the dependency FD. These two are non-prime attributes. It's easy to take it out. As you can see here, it's easy to split this. We come back to how to split these relationships a little later after we look at it. Okay. Now this split is what we are achieving. Okay, this split is what we are achieving to make sure that we are not duplicating. Okay, right. Now, what we are going to go back is I will leave this now. I will give this teaser for brain teaser for people. Okay, I actually did RAB and modified this into this. Okay, right. The argument here is that it is in 3NF or suddenly this is in is this in 2NF? It is in 2NF, right? It is in BCNF. It is not in BCNF. I think that agreement is clear. Okay. This right side, left side of the attributes are not the key to the super keys. So this suddenly is not in 3NF. Okay. Sorry, in BCNF. The question is whether this is in 3NF or not. Okay. If these are the keys, and if we apply this rule of 3NF, this is in 3NF. Okay. Right. This is in 3NF. If this is applied, for example, look at C and D. Okay. This D is part of the D is part of the key. Okay. D and A is part of the key. So suddenly the LHS of every FD is a super key. The RHS of the FD is actually a as a part of the key. So this all these dependencies are actually now the question is there a understanding mistake that we are making? That's what I want you to go and then look at. Okay, I'll revisit this. I'm purposefully creating a confusion for you to go back and look at it. I'll come back to this example again. Okay, the idea is to make you think. Okay, we are forcing you to think now. This is an example, and I want you to think about this example. Okay, right? Yes, there is. Yeah. We think the discussion is all about the dependency. Yes, actually, it is also we user one. We actually discuss the transitive dependency. I'm going to come back to this transitive dependency. Okay, and I will look at the transitive dependency in the. This is. I want you to first understand the functional dependencies. Okay. Now we are going to do in the next class an F closure. Okay, and then functional dependency closure. We did only attribute closure. We're going to do the functional dependency closure in the next class. Okay, and we are going to show you when you split a relationship R to bring it into a normal form. Okay, you have to worry about dependency preservation and lossless decomposition. These are the two things that you have to look at. That's where I'm going to introduce the transitive dependencies, because all the transitive dependencies are part of the closure discussion. So from there, we are actually going to come back and revisit this. Okay, I'm going to revisit this definition of 3NF. Okay, again when I actually do the F closure and then it from the transitive dependency part, and that closes the relational database design. Okay. So what I've shown you now is where the problem will come for 3NF and BCNF. Okay, that's where I'm showing you this example, this additional example that I've shown you here. So there is no confusion here because there is no transitive dependency. Okay, this is suddenly in 3NF. Okay, but if you want to actually take it to BCNF, this is a simple example. If I introduce the D with those additional examples, I'm actually introducing the transitive dependency. Then I have to compute the F closure for this, the functional dependency closure, okay, which will include the transitive dependencies. Okay, that we will do as the next concept in the next class. Okay, so what we want you to understand first is the requirement that BCNF with dependency preservation. Okay, and the 3NF requirement. I've introduced the 3NF requirement by saying that the RHS of the FD is part of a key. Okay, why we are doing this? I'm explaining this by saying that any change that you make here, for example, C is part of the key. If you are actually splitting this relationship for BCNF, you get this into 3NF, but then you actually violate the dependency requirement. This cannot be preserving the dependency. Okay, right? This won't be preserving the dependencies. Okay, that's the there are the requirement that when we split, take a given relationship and split it into R1 and R2. Okay, this original relationship and the dependencies are coming from the entity relationship model. This is a starting point for the relational model. Okay, ER model. This is the place where these will come from. Okay, this is the starting. Okay, for the relational database design, this is the starting point. Okay, this is the starting point. Okay, now given this is the starting point, these are the relations that are coming from the ER model. Then you're going to look at, okay, whether each of this relation is in BCNF. That's a requirement. Highest goal is to see if these are each of these relation is in BCNF. Okay, if it is not in BCNF, then what are you going to do? Then you're going to split this relationship, right? Split the relation to have BCNF. Okay. Now, when you're splitting this relationship, okay, this is where you're getting into problem. Okay. Now, let us say the original relation is split into R1, R2, R3. Okay. Now, the argument is this split is correct. This split of this relation R into R1 and R2 and R3 to bring it into proper normal form is correct. For this, to actually ensure dependency preservation, which means all FDs originally defined on R are preserved. The second one is it is a lossless decomposition. Okay, that means when you are splitting this into R1, R2, okay, R1 and R2 and R3, these will produce is a lossless decomposition. The data is not lost. If you join these relationship, you will get this original R back. Okay, then only you can split this relationship, that it is lossless decomposition. Okay, right? So in your aim to get the BCNF, you have to preserve both these things. The splits have to preserve the dependencies and it should become the lossless. Okay, so that is the reason why in this particular case, in this particular relation, if you're starting with this relation, you can easily see BCNF is not satisfied, but if you want to get to BCNF, any split will actually cause problems of dependent preservation. The AB to C cannot be preserved. That's when the 3NF comes into picture. Okay, 3NF with dependency preservation is what we're going to do. We're going to expand on this. Okay, in the next class, we're going to expand on this. Okay, I hope no, the dependency, the transitive dependencies are going to be brought in that in that next level. Okay, this is the first level of understanding of how we are doing the relational database design. Okay, in this particular case, this relaxation comes because the split will produce a problem. Okay, if you split this relation where this right side is part of a key, will produce this dependency preservation problem. That's the reason why you will stop with 3NF. Okay, this is the primary understanding. Okay, right? We will get to transitive dependencies. We will put all the three axioms for the FDs, Armstrong's three axioms for FDs, and then we will compute the F closure like we did the attribute closure. We are going to do the F closure, and we will use the F closure in the next class to see the use of dependency preservation and lossless decomposition in the relational database design. Okay, this total thing constitutes the relational database design. We start with ER model, entity relationship model. From that, we write the relationships, we write the functional dependencies, analyze each relation for the normal form, and our goal is to get all the relations in BCNF. If the relations in BCNF, we'll stop the relational database design. Okay, if the relationships are not in BCNF, we want to split the relations. But while splitting the relation to achieve the BCNF, we have to ensure that we do dependency preservation. All the functional dependencies originally defined have been preserved on the relation, and it is also you have to ensure there's a lossless decomposition. This is a necessary condition. Lossless decomposition is a necessary condition. We will, this is necessary, okay, and this is desirable, okay. We will see why this is desirable. We don't want to sacrifice on this. Otherwise, it becomes a costly way of checking for this dependency. In this particular case, you do AC and BC, AB and AC, split this into AC and AB and AC. Then for checking this dependency, you need to join this and can only check this dependency. So it becomes a very costly affair to ensure AB determines C. So this becomes, though it can be done, it is a costly way of doing it. So it is, we need to preserve all the dependencies, otherwise it becomes a costly affair for us. Whereas lossless decomposition is necessary. The R1 and R2, when I join back, I should get the original table. Okay. So lossless decomposition is necessary. You can't sacrifice on this. Whereas this is a desirable condition. Okay. Right. So we want to make all the relationships in BCNF, and then if it is not, then we are going to split the relationships, preserving these conditions. For preserving these two conditions, we need to first understand the F closure. Okay, these closure here. What are all the, given a set of FDs? What are the closure of these FDs? We will also define canonical FDs. Okay, what is the minimal set that represents the full set of FDs? Okay, that is part of the relation, and use that as a model for ensuring that the split ensures the dependency preservation and is a lossless decomposition. Okay, we're going to do both these concepts in the next class. That time we are going to revisit this. Okay, please keep this in mind. Right now we have a, no, I think this is the place where I am in. Okay, this is the slide I'm going to come back, because this is a slide where no, we suddenly know it is not in BCNF. We suddenly know it is in 2NF. Okay. The question is whether it is in 3NF or not. Okay. We are going to revisit this after we finish the FD's closure. We'll come back here and revisit this slide alone. Keep this slide in mind, and I'll come back to this slide. Okay. Right. That's the, yes, we think the discussion is all about, yeah, I'll come back to that part. Okay, next, when I do the FD closure, I will do this part again. Okay, keep this part pending. Okay, right? We suddenly know that it is in 2NF. We also know it is not in BCNF. The question is whether this is satisfying 3NF or not. So since we have not covered the transitive dependencies, I'll come back and then look at that part. Okay. In fact, I told that in the beginning. We'll come back and look at that part. Okay, right? Okay, and that time we'll also give some more examples for you to be doing it. Okay, okay, we'll stop here and come back on Friday. Okay, right? Any other questions you have? This slide, is it clear that we can't do the dependency preservation? Is this clear that it is, to bring it to BCNF, the dependency preservation will become a problem? This AB defining C, this we are going to expand on that. Okay, this dependency will cause the problems. Okay, we'll repeat this and come back to this point. Okay, yes. Okay, yeah. Okay. And then we'll go to multi-value dependency, MVD, and joint dependency. Finally, we're going to show joint dependency is the most general case, which becomes special case of multi-value dependency, becomes special case of functional dependency that we are going to build up in the next two classes. Okay, first we'll do the FD closure here, use that for doing this, and then go to the multi-value dependency. Okay, right. We'll come back. We'll come back. In the next class on Friday. Okay. Yeah. Thank you.